Rosalie Martin and I'm going to present to you MaterIA, our approach for single-image high-resolution material capture in the wild. To put a bit of context, digital materials provide 3D objects a realistic appearance by describing how light interacts with them. These reflectance properties are defined by a function called the bidirectional reflectance definition function, and these parameters, when they are not constant across the surface, are encoded into high-resolution textures, and this set of textures allow defining a spatially varying BRDF, where in addition to the reflectance properties are encoded geometric mesostructures. Creating digital materials can be done in two ways: procedural creation with a tool such as Adobe Substance Designer, that allows crafting a material by editing a nodal graph. This is very powerful, as the technical artist can decide to expose some parameters to further tweak the resulting material, but it requires technical skills and a lot of time to obtain realism. Another way is material acquisition, and in outdoor context, two main methods exist: photogrammetry, which consists in capturing a large surface from many points of view while the lighting remains constant, and photometry, which is kind of the opposite, with a single point of view but the lighting turning around the captured surface. Both methods achieve good results, but they are very demanding in terms of equipment and are also time-consuming. So there is room for improvement in the material acquisition domain, where our challenge is to provide a good trade-off between time, cost and quality, starting from a single shot with a smartphone. Material acquisition in the wild means having a solution working with a single image, allowing to capture outdoor materials with any camera device under natural lighting without the need of the flashlight. There are several challenges behind this. Working with a single image is an under-constrained problem, where it's hard to interpret a color change in the captured output. Is it due to the intrinsic color of the captured material, due to a feature that is casting a shadow, or to a small relief causing a bit of occlusion? Outdoor materials often present a highly irregular geometry that needs to be accurately captured. Natural lighting means having to handle properly the shadows and highlights present in the capture. In particular, the shadows must be removed, otherwise artifact remains when the resulting material is lit under a new lighting. This is visible here on the right column, where the scan is directly used as the albedo. We can see the remaining shadows in the render, whereas with a shadow-free albedo, we can better see the light turning around the surface. Finally, outdoor materials are often non-stationary and highly detailed, which push for the need for high resolution. To tackle these challenges, we propose a set of contributions: a cascaded neural architecture whose full capacity is focused on solving the most ambiguous task, the daylighting and the geometry extraction. We propose to bring a bit of semantic on the learning of how the light affects the color response of the material by using the illumination decomposition formula. We designed a synthetic dataset especially built for outdoor scenario, with a renderer that casts shadows and an atlas augmentation step to increase the representativeness of large shadows in the dataset. And we address the need for high resolution. We propose a per-tile approach with a seamless high-resolution blending. Our work relates to three main domains: single-view material capture, where starting from a single flashlight input, the objective is to recover SVBRDF. Shadow removal, as we deal with shadows in our outdoor context. Here the aim is to remove the shadow cast by an object, possibly outside of the picture, to get a shadow-free image. And as we propose to use the illumination decomposition formula, we also relate to intrinsic image decomposition, whose goal is to separate the reflectance and the shading component of a natural image. For single-view material capture, there are many recent research, often relying on a UNet-based architecture with some variations. Lee 2018 proposed a dedicated decoder for each SVBRDF channel, a jerking learning with a classifier, and introduced a rendering layer. As this method requires a flashlight input, there could be a remaining artifact at the position of the specular dot in the prediction. To address that, Deschamps 2018 proposed to add a global track in addition to the UNet to recover the information lost in the saturated areas. They also proposed the use of a rendering loss. Deschamps 2020 proposed a guided fine-tuning method for large-scale transfer material. It is built upon Deschamps 2018 for its generic pre-trained network, and it adds a fine-tuning step that runs on the exemplar-specific training set to finally propose a high-resolution processing of a large-scale input taken without flash with the help of small flash disk exemplars of the same input. Zoo 2021 proposed a hybrid training with both synthetic and real data, and a training with a pair of images lit differently, one being the target used for the loss. All these methods impose the use of the flashlight, which is incompatible with outdoor scenario. Also, they work well for microfacet-based material and quasi-planar surfaces, for which a purely local information is enough, whereas with shadows, we need to consider non-local information in the lighting effects like occluders. Tiny 2020 proposed a single-view normal map capture that works well in outdoor scenario. However, only the normal map is predicted. On the shadow removal domain, Q 2017 proposed to decompose the input image into a shadow mate and a shadow-free image, and proposed a multi-context network architecture to learn predicting this shadow mate. Wang 2018 proposed a jointly learning of shadow detection and shadow removal, where the shadow removal is conditional to the shadow mask detection. Also interesting, these methods are designed for the natural image domain with shadows cast by objects outside of the picture, which is different to self-cast shadows and the need for recovering an albedo, and they are not producing SVB-RDF. There are many interesting work on intrinsic image decomposition, such as U 2018 with inverse RenderNet, Leo 2019 with unsupervised learning, and Luo 2020 that adapt the surface normal knowledge for intrinsic image decomposition in indoor scenes. Here again, we have a domain and a perspective gap with the natural images. In addition, the albedo produced contains big flat tints, which is desirable for image edition and relighting, but severely lacks fine-grained details for the material domain. Let's now describe our method. We propose a hybrid approach where a cascaded neural network is trained at delighting and recovering the geometry so that the network capacity is fully used for the most ambiguous task, while the other channels of the SVB-RDF are computed by handcrafted algorithm to finally produce a high-resolution material. For the need of our neural network, we have built a synthetic dataset made of outdoor procedural materials from the Adobe Substance 3D Asset library. Starting from one procedural digital material, we have access to 4 preset variations of the exposed parameters that are defined by the technical artist that created the material, so the realism is guaranteed. We do random variations around the presets with a Gaussian distribution to explore a limited range of possibility to remain realistic while creating new variations. We then render each variation with 15 renders representing natural lighting conditions. We finally get 240 variations starting from one procedural material that we can further augment with classic cropping augmentation. A word on our renderer that casts shadows. It is made in Substance Designer. It takes the material maps in input and an environment map for computing image-based lighting. We have designed parametric environment maps to represent the sunlight and the sky, and some studio light for producing sharp shadows. The renderer outputs 3 maps, the beauty render, the irradiance map, and the specular contribution map. The irradiance map being the blending between the EBL, irradiance, and the shadow map computed with raycasting. We will use the 3 outputs as ground truth map when training. The outdoor materials of Adobe Substance 3D Asset are various and looking realistic. However, they lack samples with strong and large shadows to get a good representativeness on the domain we target. To alleviate that, we propose an augmentation step using atlases that describe small objects through SVB-RDF channels and an opacity map, and that can be splat upon the base material to produce new variations with more objects that cast shadows. Thanks to that augmentation step, our delighting network will have better chances to remove the shadows. So delighting consists in removing the shadows. Our delighting network processes small tiles separately and our architecture is based on the unit from Boubekeur 2015 with small differences. Our first attempt was to infer directly the target albedo with the L1 loss involving only the ground truth albedo. It was providing good results, but overall lacked a bit of contrast, and there were often remaining shadows in the results. To alleviate that, we introduced the use of the illumination decomposition formula, where the input is equal to the albedo multiplied by the irradiance and added to the specular contribution. The theory behind is to bring more capacity to the network and to help in decomposing the different lighting effects. Then the delighting unit has two outputs, the specular contribution and the irradiance map, for which we have the ground truth in our dataset, and the albedo is computed by reversing the formula. The loss then combines the loss for the three output maps. Here again the previous result. That is improved using the illumination decomposition for the overall contrast and the shadow removal. However, the division by the irradiance map is causing some instability, and we can observe some saturated pixels in the output at the location of the darkest shadows. To alleviate that, we introduce a third output called the enhancer map that is added to the input before applying the formula. The role of the enhancer map is to compensate the lack of precision and lost information in the input, especially in the darkest and saturated areas, due to 8-bit or 16-bit saving format. We don't have the ground truth for the enhancer map, and it is introduced once the training has already converged for the other maps to further improve the results. We can observe how it removes the saturated pixels and lightens the darkest areas. For the geometry extraction, we train a second unit that is conditioned to the delighting result, and as we concatenate the resulting irradiance map to the input to provide a 6-dimensional input to the geometry unit. The geometry unit is shallower than the delighting unit, and it outputs the normal map. We have now an albedo and a normal map predicted separately for small tiles. To reach high resolution from there, we need to remove the seam, often visible at the boundary of the tiles, as we can observe here in the albedo map. We apply a gradient domain blending by solving a Poisson system to get a seamless result. This works well for the albedo map. However, for the normal map, there can be ambiguity at the scale of a tile, where big fixture can be missed. This is the case of this big rock here, that is not well captured in the normal map. To solve this, we do a second inference at low resolution on the downscale version of the input by running the same exact network to get the low frequency normal that we blend to the high frequency normal coming from the tile to obtain the final high resolution normal map. We could do more intermediate scales, but the quality reached with this two-scale scheme is the best trade-off between quality and inference time. For the other SVPFDR channel, we run handcrafted algorithm. The normal is integrated to get the height map. We compute horizon-based ambient occlusion to get the ambient occlusion map. And we estimate the roughness map using an approximation involving the surface curvature and the ambient occlusion that provide information on the surface exposition to outdoor conditions. Our insight is that salient edges are more likely to be exposed and thus polished, while cavities are more likely to be rough. This formulation, although an approximation, is commonly used by the technical artist in the material creation workflow and allows recovering fine-grained roughness variations as the surface curvature is computed at different scales. Let's see some results now. On synthetic data first. Here the ground truth map are presented in the top row and the renderer will be used as the input of the prediction. The results are presented in the bottom row and we can observe an overall similarity with the ground truth maps that is confirmed by the resulting render. And on real pictures, here we have from left to right the input, the predicted maps, an orthographic render using the predicted maps, and a perspective render. Our render results are similar to the input with a good overall contrast and fine-grained details and a convincing geometry. Other results with a bit of vegetation. Our model generalizes well on real data, which indicates a small domain gap between our dataset and our outdoor scenario, and demonstrates how realistic are the digital materials and renders of our dataset. Here we show a 3D render of the captured material, where we apply successively the different SVBRDF channels. Initially, the input scan is rendered directly, that produces a static rendering while the lighting varies. Then we apply the extracted albedo, the normal map, the roughness map, and finally the height map. Time for comparison. We compare ourselves to Deschamps 2018 in two ways. The first one, called No Flash, uses the same dataset as Deschamps 2018, but with no flash input. And the second one, called Our Data, is retrained with our dataset, still with no flash inputs. We also compare to Tiny 2020, only for the normal estimation, as this method does not propose an albedo prediction. We can see that for both root mean square error and structural similarity metrics, our method performs best on albedo and normal maps, and produces results that are closer to the ground truth maps. Below is presented an example of the synthetic data used for this comparison. On the same sample, we show a render of the resulting SVBRDF. Here we compare Deschamps 2018 to the ground truth. We observe a darker result and a geometry not very similar to the ground truth. Here the same method but trained on our data. The albedo is closer to the target, but the geometry is still not accurate. Tiny 2020 gets a resulting geometry very close to the ground truth. However, we can observe how albedo have baked the lighting from the input. Our method shows a resulting material that is similar to the ground truth for both the albedo and the geometry. We can observe a bit of global color shift, though. We also compare to these methods on real data, where we don't have the ground truth. Here we compare our method to Deschamps 2018. Once again, we can observe the dark albedo and the blobby geometry, while our method produces a shadow-free albedo in a good color range and a geometry that looks similar to the input. When trained with our data, the albedo looks closer to the expected result. However, the resulting geometry is still inaccurate. The geometry extracted by Tiny 2020 looks very similar to the expected result. However, the input is used directly as the albedo. By rendering all these results under new lighting, we can better visualize the extracted geometry of each method. Tiny 2020 and our method produce both a plausible geometry. However, we can observe how the remaining shadows in Tiny's method are causing artifacts when the light comes from the opposite direction of the capture, while our method generates a shadow-free output. As future work, we would like to investigate in lightweight network architecture to be more easily deployable. We would like to replace the multiscale post-process blending by a multiscale network architecture to avoid possibly opposite predictions between the scales. Also, as soon as we use a 2.5 dimensional representations for our materials, some lighting effects cannot be modelized, such as the shadow that drift from the leaf in this real example, that would be glued to it with a digital material. Finally, we would like to handle metallic materials and produce a metallic map. Thank you for joining this session, and this is time for questions.